Hello, good morning, students. We are going to continue the same topic, greedy technique, where we are going to see another one, which is your which is your Huffman coding. So here you are given with a coding problem. So the coding is nothing but assignment of bit strings to your alphabet characters. So you are going to create some code words. So what are the code words? The code words are nothing but the bit strings assigned for characters of alphabet. So there will be two types of characters: fixed length encoding and the variable length encoding. Fixed length encoding is nothing but your ASCII codes, and the variable length encoding is nothing but your Morse code. So here we are going to have some prefix free codes where there is no code word is a prefix of another code word. So you have a problem. You have to check for the frequencies of the character which is occurring and what is the first binary prefix code will be seen. So here now when you go for this, you are going to see we have different algorithms. So here we are going to see the Huffman coding. So what is the Huffman coding? Huffman coding is nothing but we will be seeing how the coding works. So here you will be constructing a binary tree with the edges which will be labeled as zeros and ones, which is going to yield a prefix code of characters. So now the characters will be assigned always to the leaf node. So here the optimal binary tree, which is minimizing the expected length of a code word, is constructed by using a Huffman algorithm. So the Huffman algorithm says that initialize in one node trees with the alphabet characters and the tree weights with their frequencies. So you need to repeat the steps again and again. Maybe if there are n characters, you will be repeating the step n-1 times. We are going to join the two binary trees with the smallest weight into one and make its weight equal the sum of the weights of the two trees. So after constructing a tree, entire tree, you are going to mark the edges leading to the left and right subtrees as zeros and ones respectively. All the children will be, left edge will be marked as 0 and all the right will be marked as 1. So here you are given with a character A, B, C, D and underscore, each one is having a frequency. Now see to that, if you see this frequency, all this frequency, if you are taking, it should be equal to 1. Okay, whatever the total you are saying, it should be 1. So that is 35% of all the, this is Huffman, I will tell you what it is. This code word is used for messaging. For example, suppose if you are in some military, some confidential messages are there. So when you are sending a message, anybody will be able to read it. So what you will be doing is you will be decoding and doing the encoding also. So you will be decoding it into some ASCII codes, and finally the receiver will be encoding it, and they will be seeing, they will be encode the values and see what are the characters with respect to the message. So the confidentiality is kept or assured here because the characters are not being passed as it is. You are doing certain conversions. So here you will be having a code word where you are creating it based on what is the frequency. So in the text, maybe some 35% of the characters will be of A. B, if you see, it will be 10%. C, it will be 2%. D, it is 20%. C, it is 20%, and the underscore is 0.15, that is 15%. So put together, if you see 35 plus 1 0, 45, 45 plus 1 2 0, 0.65, 0.65 plus 2 0, 0.85, 0.85 plus 1 1 5, it is 1.000. So the total should be, that is, we are taking all the 100% characters, so it should be 1.00. So from this we are going to use this algorithm and constructing a tree structure and finding what is the code word. The code word of can be of either it can be a fixed length or it can be a variable length. Now if it is a variable length, for example, if you have the code words here, the code word is of variable length, that is, it consists of 2 bits or 3 bits. So if you want to make it as fixed, see which is having the maximum is 3. So what you do is you convert everything, you prefix with 0 and convert all the code words into fixed one by saying that the number of codes in each every code word is 3. So we have to take the average bits per character. The average bits per character is 2.25. That is for each one. You see here it is, how many are there? Only 2. So it is 2 into 0.35. Here there are 3. So 3 into 0.1. Like this, you sum up everything, you will be getting it as 2.25. So for fixed length encoding, it should be 3. But here the average bits per character is 2.25. How you are getting? You are multiplying the number of code words into the frequency and finding the sum of all these things, you will be getting it. So what will be the compression ratio? Compression ratio is for the fixed length encoding. If you see the maximum number of characters, codes in this bits in this code word, it is 3. So 3 minus what is the average bit? It is 2.25 divided by 3 into 100%, you will be getting it as 25%. So the coding will use 25% less memory than its fixed length encoding. So now how to construct it? According to the algorithm, you are going to initialize n one node tree with alphabet characters and the tree weights with their frequencies. So here you are going to have n nodes. There are 5 characters, so we have 5 nodes. Now take the least two. Which are the two? The least two are 0.1 and 0.15. 0.1 comes to the left and 0.15 comes to the right. So when you add it, whatever the parent node will be having the sum of these two, that is 0.1 and 0.15, it is 0.25. Now so you are left out with 0.2, 0.2, 0.35 and this 0.25. Among this 1, 2, 3, 4, which is shortest, the two shortest are 0.2 and 0.2. So now combine 0.2 and 0.2. Since it is of the same frequency, you have to go according to the character wise alphabets. So C comes in the left and D comes in the right. 0.2 plus 0.2 will be giving it as 0.4. Now you have 0.25, you have 0.35, you have 0.4. So next what and all to be added? The next to be added is 0.25 and 0.35. 0.25 and 0.35 you have to add it. So 0.25 is less, so it comes in the left child, and 0.35 is greater, it comes in the right child. So when you add, what you will be getting it as? You will be getting it as 0.6. So what you will be doing is you will be having 0.6. 0.6 will be your root node, and that is been obtained how? By 0.6 is obtained by taking 0.25 and point, here you will be getting it as 0.25, and the right will be having it as 0.35. Okay, so 0.25 plus 0.35, it is 0.6. So now what are the two things left out? After completing the entire thing, you are getting it as 0.6. So you are now left out with only 0.6 and 0.4. So when you say 0.6 and 0.4, 0.4 comes as the left. So you can have a tree like this. You will be saying it as this side you will be having 0.6, 0.6, 0.6 in the right and 0.4 in the left, and you will be getting it as 1.0. 0.4 plus 0.6 you will be getting it as 1.0. 0.6 you, how you got, you are adding 0.25 and 0.35 as how we have taken here. We will be seeing that. So you will be saying it as 0.4 plus 0.6, you will be getting it as 1.0. So now when you go for this, what you have to see, you are now having everything, and we will be saying that whenever you go for the tree structure, what is the next is, the next will be having, if you see, you will be seeing it as this is your tree structure. So in this tree structure, if you see what is being taken, 0.4 is taken as the left, we have already seen. 0.6 is taken as the right. Why 0.6 is right? Because 0.6 is having a higher value. So you will be saying it as 0.6 is by taken 0.25 and 0.35. So now it is 1.0. So 1.0 you have, this left is your 0.4, right is your 0.6. 0.4 is obtained by adding 0.2, that is C, and 0.2 D. 0.6 is obtained by taking 0.25 and 0.35. 0.25 is obtained by adding 0.1 and 0.15. So this is your entire tree structure. Okay, so now when you see this, you have understood that how you got it. Now, from this tree, you mark all the left. So here it says, what is the next step? You mark all the edges leading to right as 0 and all the right as 1s. So that's what we are going to do here. So all the left edges are marked as 0. Here this is the right child, so 1. Here again this is right child 1, this is right child 1. This is left 0, left 0, 1. So now for example, if you go for the leaf node, all the leaf nodes are, you can see that all the leaf nodes are having the characters. Now from the root node till the leaf node, find out what is the edge labels. For example, if you see C, from the root node till C, so that is 0, 0. For C it is 0, 0, here it is there. Next, for D it is 0, 1. So D it is 0, 1. Now for B it is 1, 0, 0. So B it is 1, 0, 0. B can find out it is 1, 0, 0. Next for underscore it is 1, 0, 1. So for underscore it is given as 1, 0, 1. What is A? A is 1, 1. So here you have for A as 1 and 1. For C it is 0, 0. It is there. For D it is 0, 1. It is also there. So from the root node, you are going till the leaf node. All leaf node, you can see that it is nothing but it is the character. So from the root node till the leaf node, if you see what is the edge values, the edge values will give you the code words. So here it is in different levels. It can be in the next level also, it can be something, it can be there. So all leaf nodes, if you see, all the leaf nodes are nothing but it is considered to be the it is the code word. So that's what here we are saying that, see what is the maximum number of code codes in the code word, it is 3. So here we are calculating what is the average bit per character, what is the fixed length encoding, what is should be the compression ratio, and what is the memory capacity taken for this coding word. Less memory occupied. Why? Because we are using the variable size. If fixed means all, instead of 2 bits, we have to represent everything. Here some of them, at least only 2 characters are having 3 bits, others are all 3, but if you make it as fixed length, all should be made it as 3. So that's what you have for the Huffman coding. So Huffman encoding is considered to be the one of the important file compression methods. Now the drawback can be overcome by something which is called as the dynamic Huffman encoding. So why? Because supposing if you want to add any character, if you are adding any character in this, your entire tree structure will change. Okay, we cannot, in between we cannot add it. Suppose if you want to add it, we have to add it in the beginning itself. This is called as the static one. But you can also, the drawback can be overcome if you use a dynamic Huffman encoding, in which the coding tree is obtained each time a new character is read from the source string. So the Huffman code is not limited to the data compression. Okay, data compression, you have a formula summation I equal to 1 to n li into wi, where li is considered the length of the simple path from the root to ith leaf, where wi is nothing but the weighted path length. So it can also be used for some game applications. The game for guessing can be used like zeros and ones or yes or no, something like that can be used. For example, suppose if you have a tree structure like this. So if you want to choose a value from 2 to 4, 1 to 4. So what we are doing, we are having checking for whether n is greater than 2. If n is greater than 2, next we will check whether n is greater than 3. If n is greater than 3, obviously the value will be 4. Otherwise it will be 3. Similarly, if n is greater than 2, no means it will check whether n is greater than 1. Yes, it is greater than 1 means then n is equal to 2. Or else it will be, if n is not greater than 1, no means it is. The tree can be of either of this form, or here we say it as the root node itself, it's taken as the last value. What is the last value? You are checking whether n equal to 4. If n equal to 4 means yes means n equal to 4. No means you are checking whether n equal to 3. Yes means the answer will be 3, or else no means answer will be equal to 2. So again, if it is equal to 2, no means you are saying n equal to 1, or else you will be saying it as n equal to 2. So the example of the decision tree is basically based on how you are going to have the tree structure for the game application. So here for each and every game, by asking a question, we will be finding the length of the simple path from the root to a leaf in the decision tree, which will be based on the number of questions needed to get the choice. So here, if number I is chosen with the probability PA, then we can say it as the sum is nothing but summation of I equal to 1 to n li into PA, where li is considered as the length of the simple path from the root to the ith leaf, which will be indicating the average number of questions needed to guess the chosen number with a game strategy represented by its decision tree. So if each of the numbers is chosen with the same probability, then the best strategy to successfully eliminate half the candidates at the binary search. So here, when you see it, you will come to know that when you have the Huffman code, it is a coding which is used for the bit strings to alphabet characters, and you have the bit code words. Bit strings are sent for characters of alphabet, and there will be of two types. One is fixed length and another one is variable length. So here, if any of the problem, if it is asked the frequency of the character occurrence, you can finally construct a tree structure and find out what is the code word. So if it is asked for the fixed length encoding, then you have to convert the code word into fixed one by prefixing it with some zeros. Okay, so either it can be asked as a theory question or a problem means you will be given with all the characters. Ensure that whatever the frequency it's given, it should be exactly, if the sum of all the frequency should be equal to 1. Because we are saying that we are taking all the 100% characters and seeing what is the occurrence of it, whether it is of the percentage of occurrence of each character has to be determined from this text character code word. So this is one of the algorithm. There are various algorithms given for code word or encoding and decoding. So you can choose anyone based on how it is used in some computer networks. Also, if you say there is a Huffman coding algorithm which you would have studied in your previous semester for the computer networks. So based on that, you have to create everything and you need to find out. So thank you guys. This is about the Huffman code. So this is taken from the greedy technique. So in the next class, we will be seeing, we'll just revise about what are the problems we have seen in the greedy and the dynamic programming technique. Okay. Hope you are clear with the problem which has been given. You can take some problems and see how it can be solved.